Okay, so we start today's lecture. Okay, so we have the last theorem for section 2.2 to prove. Okay, in last Friday, we proved in theorem 2.2.8 that if we have a k-dimension affine space in Rn, then we can create a system of linear equations. Actually, a system of n minus k linear equations in n unknowns to describe this affine space. And now the theorem here gives us a version of the converse. So suppose we have a system Ax equal to B of n minus k linear equations with n unknowns. Right? So such a system represents a k-dimensional affine space in Rn if and only if the rank of A, the rank of the coefficient matrix, is equal to n minus k. Right, so it provides us an if and only if condition. All right, so here is the proof. So we let U, C be the reduced row echelon form of the augmented matrix. A, B. All right, so, and it is clear that U, the U, is the reduced row echelon form of A. All right, so we know that from chapter 1. Any questions? All right, so if no questions, then we'll prove the big word part first. So we'll prove that if the rank of A is n minus k, then this linear system represents a k-dimensional affine space in Rn. All right, now, since the rank of A is n minus k, so they are n minus k pivots in the reduced row echelon form of A. Okay, so we have n minus 1 pivots. Okay, so now without loss of generality, Right. So without loss of generality, we can we assume that the first n minus k columns of U contain pivots, and the rest k columns do not. Okay, so let me draw the augmented matrix in this way. We have 1, 0. Okay, so we assume the first k columns contain pivots. Right, so this is first k columns, and the rest, the first n minus k columns. Okay, so this is n minus k times n, and this one is n minus k times 1. Right. Now the rest k columns, we write it as 1 n minus k plus 1 u to n minus k plus 1 u n minus k plus 1. This is u 1 n u 2 n u n minus k and here, and C1, C2 up to Cn minus k. Okay, so without loss of generality, we assume we have the reduced echelon form in this format. Any questions? Now, because the last k column, so we have this is n minus k columns, and here we have k columns, and these k columns, because they do not contain any pivot, so they can be selected as free variable. So the corresponding unknown variables, x n minus k plus 1, up to xn, can be selected as free variables. All right, so this is the point. Okay, they can be taken as free variables. So once that, so we have, so now we have, okay, x1 equal to c1 minus u1 and minus k plus 1, x and minus k plus 1 minus minus u 1n xn, and the x2 corresponding, the x2 is the unknown variable according to the second column. So x2 is equal to c2 minus u2 n minus k plus 1, xn minus k plus 1 minus minus u2n xn, etc. up to xn minus k equal to cn minus k minus u n minus k plus 1 x minus k plus 1 minus minus u minus k minus k minus kn and xn. Okay. And the solution set, okay, of the linear system Ax equal to b consists of all vectors okay in Rn of the form so the form is that x1 up to x minus k and x minus k plus 1 up to xn. Okay, so we just put it here. So we have c1 minus u1 minus k plus 1 minus u1n xn that c minus k minus u minus k minus k plus 1 minus u minus k and xn here, and x minus k plus 1, because x minus k plus 1 up to xn are free. They can be arbitrary, so they are free. Okay, they are free. Okay, and so that we have c1 c minus k 0 0. So this is the constant vector there, plus the free variable x minus k plus 1. All right, and minus u1 minus k plus 1 minus u minus k plus 1 and the 1 and the 0 plus xn minus u 1n minus u minus k n 0 1. All right, so the solution set becomes to that one. Well, x minus k plus 1 up to xn in R. So they are free. All right. Now, to show that this solution set represents a k-dimensional affine space, we have to show that the vectors associated with the free variable, we have k vectors there, right? they should be linearly independent. Okay, so we have to check whether they are linearly independent. Now, so if we have a linear relation, okay, on the ordered state. Okay, so on the ordered state, so the first one here, this column vector, minus u 1 minus k plus 1, minus u minus k plus 1, that 1 0. The last one, minus u1n, minus u minus kn 0, 1. Okay, so if we have a linear relation on the ordered state, okay, so let a linear relation is here, 0 vector is equal to alpha 1 minus u1 minus k plus 1, minus k plus 1, 1 0 plus alpha k u minus 1n minus u minus k n 0 1. Okay. So suppose we have a linear relation. So this is a linear relation, and alpha 1 up to alpha k are scalars. And this linear relation can be combined together. So this is minus alpha 1 u1 minus k plus 1 minus minus alpha k u1 n minus alpha 1 u minus k plus 1 minus alpha k u minus kn, and here is alpha 1 up to alpha k. Now, this vector is equal to 0, where it implies that alpha 1 equal alpha 2 equal alpha k equal to 0. All right, so any linear relation on this ordered state must have coefficients to be all zeros. Okay, so this shows that the ordered state okay, so this ordered state minus 1 and minus k plus 1 minus and minus k and minus k plus 1 1 0 minus u 1n minus u and minus kn 0 1. Okay, so this say it's linearly independent. Okay, so we have shown that, okay, these k vectors are linearly independent. Okay. So the conclusion is that, and then the solution set of our linear system AX equal to B is a k-dimensional affine space in Rn. Okay, so this is the reverse part. So we have proved that if the rank of A is n minus k, then this linear system represents a k-dimensional affine space, because the solution space of this linear system, okay, has this parametric representation here. Questions? So this is the reverse part of the theorem. Any questions? Okay, so now we will prove the forward part. Okay, to prove the forward part, this part is P implies Q. So this is equivalent to not Q implies not P. Okay, so we will use this strategy. So we now assume that all right, so we now suppose the rank Ka is not equal to n minus k, right? Because the forward part asks us to show if such a linear system represents a k-dimensional affine space, then the rank of A is n minus k. So now we assume this is not true. Okay, so suppose that the rank of A is not equal to n minus k. Now since A has n minus k rows, if we define the rank of K as R, then the R must be less than right? So must be less than n minus k, because it's not equal to n minus k, right? But theorem 1.3.7 says that the rank R should be upper bounded by the number of rows, which is n minus k. All right, so R is less than or equal to n minus k, but here we suppose that the rank is not equal to n minus k, so that R is less than n minus k. All right, so then the first R rows of the reduced echelon form of A contains pivots. And the last n minus k minus R rows of U are 0 rows. Okay, 0 rows. All right, so the U here, so the last if the last column C of the augmented matrix C UC right? So if the last column of this augmented matrix contains a pivot, okay, contains a pivot, then the linear system AX equal to B is inconsistent. Okay, inconsistent. And the solution set is the empty set. Okay, so in this case, the linear system AX equal to B does not represent any k-dimensional affine space. Okay? A contradiction. Because we assume that the linear system represents a k-dimensional affine space there. Okay. So that if the last column of the augmented matrix contains a pivot, then the linear system is consistent. So of course, it cannot represent any k-dimensional affine space. Now, and if the last column C does not contain any pivot, then the linear system AX equal to B is consistent. All right? It's consistent. Now, in this case, without loss of generality, we assume that the first okay, so the first columns of U contain pivots, and the last, and the rest, and the rest, n minus r columns do not. E in this term, U C becomes 2, 1, 0, 0. Okay, so now the augmented matrix becomes true in this format. Okay, so now the the corresponding n minus r unknown variables xr plus 1 up to xn can be selected to be free. Okay? So they can be selected to be free. Okay, so that the solution set of the linear system Ax equal to B is an n minus r dimensional affine space. In Rn, okay, as illustrated in the proof of the reverse part. Okay, so with the similar argument, we know that because we can set the n minus r unknown variable to be free, so the solution set is an n minus r dimensional affine space. All right, now, since n minus r is greater than n minus k, okay, because r is less than n minus k, so n minus r is greater than n minus k, which is equal to k. Okay, so n minus r is greater than k. So the linear system, so Ax equal to B, right, does not represent any k-dimensional affine space. So a contradiction again. Okay, so we have no way to go, and so that means that the rank should be equal to. Thus, we conclude the rank of A should be equal to n minus k. Okay, so that is the end of the proof. Questions? All right. So if no question, then I will move on to the next section. All right, we'll talk about linear transformation. All right, linear transformations are special kind of functions. And so I am a little bit worried about your understanding on functions in general. So I would like to spend some time to review the concept of functions. Well, if you do know function very well, then you can take a nap right now for some time. Otherwise, I would like you to pay attention to my discussion, because my discussion is very general. So let A and B be two sets. The symbol, as is well known, so the symbolism F with the column A to B. All right, so this is symbolism. Signify that F is a function. Sometimes people say a mapping from set A to set B. All right, now this means that with each element x in A, in the set A, a single particular element y in B is associated. All right, so we call y the value of f, the value of the function f at x, and denote y equal to f of x. Okay, so they are just basic language of a function. For a function, A is called the domain of the function f, and the B is called the codomain F. Okay. Now, the range denoted as f of a of the function f is the set consisting of all possible values of f, i.e., the range of A is defined to be all the elements in the codomain such that y is equal to f of x for some x in the domain. And of course, the range of a function f of A is a subset of the codomain, right? Not necessary that range equal to the codomain, right? But the codomain should include the range. Any questions? Now, a function f from A to B is called one-to-one or injective if f of x equal to f of x prime implies x equal to x prime. So if the function has equal value at two elements, x and x prime, then these two elements must be the same. Okay? It's called one-to-one. The other way to say it is that if x not equal to x prime, then f of x should be different from f of x prime. It implies, okay, right? It's about one-to-one function. A function is called onto our surjective. If the range of A is equal to the codomain. Last one, a function f from A to B is called one-to-one and onto or bijective. So bijective is the combination of injective and the surjective. So it's if f is both one-to-one and onto. Okay, so these some properties. Next one, I would want to define composition of functions. So let's f from A to B. So f is a function from A to B, and the g is another function from B to C. Then the composite, right? The composite denoted as G circle F of F and the G is defined as a function from A to C by this way. The composite of F and G on an element X in A is defined to be G of F of X. Okay, and so there is a diagram for that. So A to B by the mapping F, and B to C by the mapping G. Now the composite from A to C has the phenomenon that X goes to F of X and then goes to G of F of X. So together is X goes to G of F of X. Okay. Right. So that is about the composition of two functions. Composition of functions has some nice properties. Now, let H is another function from C to D. Now it can be seen okay, you can do the composition, all right, of F and G, and then do again a composition with. So the composite, this composite will do composition with H again. All right, this is one way. The other way is that you can do the composition of G and H first, and then you do the composition of F and this composite. Okay, so this is a kind of associated law. So this is an associative law of function of composition of functions. Okay, so we have an associative law of composition of functions. So the order of composition does not matter. Okay, the order does not matter. You can do this composition first and then this one, or you can do this composition first and then this one. Okay. But a remark. composition of functions is not commutative. So it's possible that G equal to G. Okay. Sometimes maybe if this is defined, but this may be undefined. Okay, because the codomain may not be equal to the domain of F. Okay, so composition of functions may not be commutative, but the associative law is always true. Now, for a set for a set A, the function IDA from A to A defined by ID of X is equal to X. So X mapped to X. It's called the identity function on A. Okay, so every set A has an identity function on itself. It is clear that any identity function is bijective. So any identity function is one-to-one, of course, and it's onto, right? So it's bijective. And for a function f from A to B, we have the following nice composition. So the identity function of A composite with the f function is the same as f, okay? And if f is composite with the identity function of B, then it's also f equal to f. The reason why we put the identity function on A and even on B there in different right hand side, left hand side is to we have to accommodate that for composition the codomain should be equal to the domain here of the second function. Okay. Now, a function f from A to B is called invertible if there exists a function G from B to A. Right, so this is G from B to A, such that the composite of F and G is equal to the identity function on A, and the composite of G and F is the identity function on B. Now in this case, G is called an inverse of F. All right, and we have a quick lemma, 2.3.8. If G and H are inverse functions of a function f from A to B. So suppose f is invertible and f has two inverses, f and G and H. Then these two inverse functions must be equal. Okay. Now, all right, so since G and H are inverse functions of F, so we have the following data. We have G, F is IDA, F, G, B, H, IDA, F, IDB. Okay? From the definition, when we have invertible functions, then that we have these properties. Now, G is equal to G, a composite IDB. Okay. Remember, G and H, they are functions from B to A, okay? Because F is from A to B, so G is from B to A, H is also from B to A. Okay. So G, the domain of G is B. Okay. So G is equal to G coupled with IDB. Okay. So this is it's called the unity property. But anyway, we have that. Okay, so G circle. But IDB, we use this one. Because IDB, the identity function is F circle H here. And by the associativity, so by the associative law, So this is G, circle F, and then H. But G circle F is IDA, circle H. But IDA is equal to H. And then we have done. So G equal to H. Okay, so that's an invertible function f from A to B has a unique inverse function. And we will denote this unique inverse function as f minus 1, which is from B to A. Okay, so if f is an invertible function, then its inverse unique and will be denoted as f inverse here. Wow. Okay. Now we will give a necessary and sufficient condition for a function to be invertible. So a function f from A to B is invertible if and only if it is bijective. Okay, it is bijective. You all know this theorem and use that a lot, especially in high school. Right? I think I have time to finish the forward part. Okay, so the forward part says that when a function is invertible, then it should be bijective. Right? So assume that f is invertible. Okay, now consider x prime in A such that f of x equal to fx prime. So consider two elements in A such as they have the same value. Then we apply inverse function of f on both sides. And this is implies that x is equal to x prime. Okay, so f is 1 to 1. Now, for a y in B, y can be written by the identity function. Okay, so y is equal to the function value of identity at y. And this is f. But identity function B is equal to the composite of f inverse and f. So this is f of f Okay. So y is a function value at this element. So we let x equal to the value of the inverse of f at y, then y equal to f of x. So that is in f of a. So for any y in B, we find that y is in the range. So we have B is contained in the range of A. Because every member in B is in FA. But we know the range of A should be a subset of the codomain. So the range is equal to B. And F is onto. Okay? Okay? So we finish the forward part. So when F is invertible, then F is bijective. I have 2 minutes left, but I think I can't finish the river part. So I will finish the reverse part on Friday. Okay, so let's take a break before we take the quiz number 3.